Okay, so today we will start from integration with unequal segments. So up to now we have discussed the methods in which the segments were equal, but there can be a situation when the data which you will obtain uh, will be with unequal segments. So in those situations, how you will integrate it? So the first method for this type of integration will be the use of trapezoidal rule. So in the trapezoidal rule, the formula for each segment will be applied like this. So in this case, for the first segment, the length of the segment will be h1, and its endpoints will be x0 and x1, and their corresponding functional values will be averaged and then multiplied with this with their segment length. And similarly for the other segments. So in this case, you will add the area under all those segments, and then you will get the answer. So let's see it with the help of this example. So suppose we have the data for this function, 0.2 plus 25x minus 200x, and then so on. But this data is now at unequal segments. So 0, 0.12, 0.22, 0.32. So there is in the the length of the first segment is 0.12. The length of the second segment is 0.1, and so on. So the length of the segments are changing. So then in this case, how will we find the area under this curve? How will we integrate it from 0 to 0.8? So in this case, then you will integrate it segment by segment. So you will take the first segment whose width will be 0.12. As you can see, 0.12 minus 0 is 0.12. And its end points are 0.2 and 1.3. So these are the functional values. So for example, if we put x is equal to 0 into this equation, we get this value. If we put x is equal to 0.12 into this equation, then we get this value, okay, 1.309. So 0.2 plus 1.3097, and then you will divide by 2. So you will get this answer, and then so on, you will add it. So let's see it in this Excel. Okay, so I have input this data over here already. So for example, this is these are the data points. Although you can calculate these values of fx from the equation of the polynomial given, but I have just entered them as here. So we can now do the calculations. So next step, if you do it in Excel, can you see the Excel over here?
Yes.
Okay. Next, next step in Excel will be to find the value of h. So we can find the value of h like this. So h, or maybe we can start from here. Yeah, h is equal to this value minus the previous value of x. Okay, the value of x at here minus the value of x at the previous point. So it will be 0.12. And then in this way, now it is using Excel, we can find the values of h. Okay. So here you can see that the values of h are 0.12, 0.1, 0.1, 0.04, 0.04, 0.04, 0.1, 0.1, 0.6, and 0.1 again. So the values of h are changing. Okay, the values of h are changing. Okay, so now the next step is to find the uh, the next step is to incorporate the formula. So for example, fx naught plus fx1 over 2. Okay. So for h1, what will be fx naught? That will be the previous value. Okay. And fx1, that will be the same value at that level. So in this case, uh, now, if we want to find this, that is fx 0 plus fx 1, okay, like this. This is just for our indication, okay, this value, okay, average. So then what we can do is, so we can take this value, this will be fx naught, and then this will be fx1, and then divided by 2. So we will get this value. And similarly, I can add it. So what I can do is, now I will multiply these one. Okay, I will multiply these values and then add up all these values. So then we can find the product. Okay, product is find the product of h and this value fx naught plus fx1. Okay, and we can simply say that the product, okay, product of these two columns. So it will be 0.12 multiplied by this. We get this value, and then we copy it down, and now we will find the sum of the product. Okay, sum of product, that is, sum of the product will be equal to sum. Okay, or we can use the auto sum here. So we get 1.5948, the answer. Okay. Or in Excel, you can even get this answer directly as by this formula as well, sum product formula, sum product. So in the sum product, we will first put this array, and then I will put second array. So in this case, Excel will multiply the corresponding values of these arrays and then add them together. So it will also give us the formula directly as well. Okay. So we can do it in a long way, or you can do it in a short way. So the both way you can do it. Okay. So 1.5948 will be the answer in this case. As you can see that the same answer has been obtained by 1.594801. So which represents an absolute percentage relative error of 2.8%, because the true answer was something like 1.6405, okay, by the integration. So because this is the same example as this is the same data for the example as we did before. The correct answer was 1.64. So if we find the percentage difference from 1.64 640533, so that will be 2.8%. The true true answer is 1.64 0533. Okay, so the true percentage error will be equal to this true value minus the calculated value divided by the true value and multiplied by 100. So it will be 2.78% in this case, 2.78% error. Yeah, 2.78 is the same as 2.8% in approximate terms. So this is how you deal with the unequal segments. A further inspection of this data shows that uh, not every segment is unequal. Some of the segments are, some of the adjacent segments are equal as well. So for example, if we see that in this data, after the first two segments, okay, uh, so for example, this one, and then after the first three segments, the next three segments are equal, okay, and then these two segments are equal, and then they are unequal again. So in this case, what we can do is we can further improve the accuracy by applying by successively applying the uh, equal segment rules, which are more accurate. So for example, 1/3 rule and a trapezoidal rule. So for example, in this case, example 21.8, what we can see is recompute the integral for the data in table 21.3, that is this table. Okay, recompute the data again, but use Simpson's rules for those segments where they are appropriate. Okay. Uh, in this case, what we can see is that the first segment is evaluated with the trapezoidal rule. Because the next two segments from x is equal to 0.12 to 0.32 are of equal length, their integral can be computed with Simpson's rule. So if you can see that the next segments from x is equal to 0.12 to 0.32 are equal length. So for example, these are uh, 0.12 and 0.12. So here we can apply the Simpson's rule. Okay. Yeah, here we can apply the Simpson's rule. And the next three segments are also equal, and as such, uh, they may be evaluated with the 3/8 rule to give I is equal to this one. Why 3/8 rule in the next three segments, and why Simpson's 1/3 rule in the two segments? Why not we just apply the same rule? Why do we? Why are we changing the rules? Hello, can anyone answer? So it is 2.24887. 2.24887. So here we have applied the mixed method. Okay. So here in this case, we applied the uh, mixed method, in which case we applied the trapezoidal, Simpson's is 1 by 3 and 3 by 8 rules. Okay. So for looking at this data, so the trapezoidal rule applies to the first segment, then Simpson's 1 by 3 rule apply to the second next two segments, Simpson's 3 by 8 rule apply to the next three segments. Then again, Simpson's 1 by 3 rule apply to the next two segments, and for the last two segments, trapezoidal rules is applied. So by the application of these rules, we calculated these values, okay, by applying the formulas, and then we added them together, then we got the answer of 1.6036664. And in this case, the true percentage error is 2.24%, which is smaller than in the previous case. So in this case, what we can assume, what we can say is that in the case of the unequal segments, we can even, there may be a possibility depending on the how uneven data we get. There may be some data in the uneven data that may be uh, evenly distributed. So we can apply a mixed method. So by the mixed method, maybe we can increase the uh, accuracy of the answer as well. Okay. So that was the application of the unequal uh, data with the Simpson's rule, with the inclusion of Simpson's rule. So inclusion of Simpson's rule is better because Simpson's rule is much accurate than the trapezoidal rule. So therefore, whenever possible, there's a possibility for the inclusion of the Simpson's rule, we can apply it. Okay. So these were the close integration formulas. So trapezoidal rule, both the variations of the Simpson's rule, these were the closed integration formulas. There are other formulas as well, which are called as the open integration formulas. So in the open integration formulas, the integration formulas have limits that extend beyond the range of these data. So this table summarizes these formulas, but because of the limitation of the time and application, we will no longer be uh, studying these formulas, which may be, I think, which may have some application in the forthcoming chapters as well. But there is only a mention of this open integration formulas over here. So we can apply these formulas. So it's corresponding to the closed integration formulas. These formulas also can be applied, and they also have their increasing accuracy by which is obtained by increasing the number of segments which are considered in each application or iteration of the formula. Okay, so with this, this topic is completed, and now we can start the next topic, which is about uh, uh, the solution of numerical solution of differential equations. And for the numerical solution of the in this solution topic, we will only be considering the numerical solution of the ordinary differential equations. Okay, so do you have any question about uh, the previous topic?
No.
Okay. Okay, so if you remember that your last course, most of you have taken the last course on the differential equations and linear algebra. In that course, a lot of part was about the differential equations. And in that topic, we only considered the analytical solution of the differential equations. However, many differential equations cannot be solved with the analytical solutions. So therefore, we need to solve them. We need to solve them with the numerical solutions. So the numerical solutions for the differential equations uh, have a generalized name, and these generalized name, uh, the uh, the methods are called as the Ranjekata methods. Okay, Ranjekata methods. So so this is about the chapter number 25. So due to the limitation of the time, we will only be considering one chapter for this. So this is actually your last chapter of this course. And in fact, it's a little bit lengthy chapter. So uh, it will cover like this week and also maybe the next week as well. And we still have one more week after that. So today we are in the week 12, then the next is week 13, and then there will be week 14. But week 13 we will finish this topic, and week 14 we can use for a revision. Okay. So these are called as the Range Kata methods. Okay, Range Kata method. So it's a little bit strange name. So maybe uh, someone someone can read it as like Runge Kuta methods as well, but it's actually I think the correct pronunciation is the Range Kata methods. Okay, Range Kata methods. So or it's short. We call also the short for this as RK methods. Okay, so sometimes we also say them as the RK methods. Okay, so what are these RK methods? The simplest of the RK methods is the Euler's method. Okay, so maybe I can show it from the book to you. Euler's, so chapter number 25. Yeah, yeah. So chapter number 25. So Ranjya Kata methods. So in this chapter is devoted to solving ordinary differential equations of the form dy over dx is equal to f of x y. Okay, remember that the ordinary differential equations are of this form. The differential equations are those equations which have the derivative term in them. So derivative term is dy over dx, and all the other terms will be a function of those function of those dependent and independent variables. So in this case, we assume that we see that uh, x is a independent variable, y is a dependent variable. So and there is a numerical approach for solving these types of equations. So because from calculus we know that dy over dx actually represents the slope. Okay, dy over dx represent the slope. So if, for example, if we have this dy over dx, and if we have a function of x, y, so that function of x, y will be a curve. Okay, function of x, y will be a curve. So suppose it is this curve. Okay, and if on this curve, if you take a slope at some point over here, if you take a slope at that some point over here, and then we go along in the direction of that slope, then we get when then we can reach to another point. Say if the initial point was xi, the next point will be xi plus 1 some point, and then that point on the slope, that point on the slope will be a new approximation for the for the curve. Okay, according to this formulation, and it will be a new approximation on the curve. So this gives rise to a family of methods which starts from the Euler's method approach. So the Euler's method is same like this approach. So in this case, if by the Euler's method we predict the function, that is, if we predict the function, then we predict this function by the slope method. Okay, we take the slope and then we take the value on that slope equation, uh, uh, which is represented by the tangent line to that curve. Then we get the value of the new function. Of course, in this case, there will be an error. So if the true error value will be here, the predicted value will be here, and then there will be an error. But this determination of the error will give rise to some more refined methods, and these techniques are generally categorized under the Ranjekata methods. Okay, Ranjekata methods. So, in the Euler's method approach, what we see is uh, so we have uh, these methods, and then in Euler's method approach. So let's see that we can go to this here. So in the Euler's method approach, what we see is that the first derivative provides a direct estimate of the slope at xi. So, so this was the this is represented by phi is equal to fxi yi, where fxi yi is the differential equation evaluated at xi yi. So this estimate can be substituted into this equation, the previous equation, which is the equation for the line. Okay, this is the equation for the line, and then this gives, by substituting this equation into this over here, this formula is referred to as the Euler's or the Euler-Cauchy midpoint, Euler-Cauchy or the point slope method. So a value of y is predicted using the slope equal to the first derivative uh, at the original value of x to extrapolate linearly over the step size of h. So this is, in words, we can represent the Euler's method. Remember, okay, remember that solution of a differential equation is in terms of a curve, and that curve we can represent, we should be, ideally we can represent in terms of y is equal to some value. Okay, y is equal to some value. So therefore, as you can see that in this Euler's method, we get y is equal to yi plus 1 is equal to yi plus f of xi plus yi plus 1 into h. Okay, so this formula is referred to as the Euler's method. Okay, so let's apply this formula first, the Euler's method. So in this problem, we take an equation, a differential equation, dy over dx is equal to minus 2x cubed plus 12x square minus 20x plus 8.5. Okay, so what we can do is I can take this equation. So for example, the equation is, differential equation is uh, dy over dx is equal to minus 2x cubed plus 12x square minus 20x plus 8.5. Okay, so first see what is the analytical solution. Analytical solution. Okay. So the analytical solution is, if we, for this analytical solution, we will integrate it. Okay. So we will integrate it. So integrate this value. Okay. And by the integration, what we will get is minus 2x power 4 over 4 plus 12x cube over 3 minus 20 x cube over 2 plus 8.5 x. Is it correct?
Plus C.
And plus
Should it
c.
be squared?
And it should be 20x square. Okay, so it will be minus 0.5 x power 4 plus 4x cube minus 10x square plus 8.5 x plus c. Okay, so that will be y. So we need to integrate it from x is equal to 0 to x is equal to 4 with a step size of 0.5. The initial condition at x is equal to 0 is, so the initial condition is uh, y0 is equal to 1. Okay, at x is equal to 0, y is equal to 1. So which means that y is equal to 1, and then all these values are 0 plus c. So c is equal to 1. So the value of c will be equal to 1. So this will give us the solution as 0 minus 0.5 x power 4 plus 4x cubed minus 10x square plus 8.5x plus 1. Okay, so this will give us the solution. So this is the numerical solution. But we have to estimate. So we have to, by Euler's method, we have to estimate y from x is equal to 0 to 4 at intervals of 0.5. 0.5. Okay, so we have to interval. So equation 25.2, that means for the Euler's equation is, what is the Euler's equation? Euler's equation is yi plus 1 is equal to yi uh, plus f of xi plus 1, sorry, xi yi times h. Okay, so we have to apply this equation. So yi plus 1 we have to calculate. Yi is, so because yi is, these are the initial values. So yi is equal to 1. Okay, yi is equal to 1. And what is f of xi? What is xi? Xi is 0. Okay, f of 0, and yi is 1. So what is f0 1? So because this is the equation given as, this is the value for this will be equal to, because value of x will be put as 0 0 0. Okay, and then it will be 8.5, and h is equal to 0.5, which is the interval is 0.5. So therefore yi plus 1, that is the next value. That means in this case, if I plus 1, that is y at a value of x is equal to 0.5. Okay, that will be equal to 1 that is yi is 1 plus the 8.5 into 0.5. So this will be equal to 5.25. Okay, 5.25. So in this case, the Euler's method gives us the value of 5.25, but the original value is, so original value we can get from here. Okay, so which is equal to y is equal to minus 0.5 into 0.5 power 4 plus 4 into 0.5 cube minus 10 into 0.5 square plus 8.5 into 0.5 and plus 1. So this is equal to 3.21875. So now what we have got over here is, so this is the true value, that is the true y 0.5, and then this is the from the Euler's method. But here you can see that the error is 3.21875 minus 5.25. So the error is minus 2.03125. Okay. So, and in this case, that is the, in percentage terms, this error is 3.21875 minus 5.25 divided by 3.21875 times 100, which is equal to minus 63.1% error. So you can see that by this Euler's method, we get quite a lot of percentage error in this case. So the same thing which I have done over here has been done on this in this example as well. So here you can see that this error which we got is 63.1%. In the second step, we can repeat it. So in the second step, we will use this predicted value of y in this formula, and then we will get the value of the function from this predicted value of x and y. Okay, and then we will get the further answer over here. So in this case, we will get 5.875, and this the true solution is about 3 over here in this at this case. In this case, the true percentage error will be 95.8%. So in this way, this process will be repeated, and then we can get the values, the Euler's values over here, and then for each case we will get the global percentage error over here, and then we will can also find the local percentage error over here. I will talk about this local and global percentage errors in little bit detail later on in my next lecture. Anyways, I just started this topic over here, and then I think this topic will continue for the next at least 4 lessons. Okay, so we will complete it later on.